This is the SR-71 Blackbird. It flew faster than a rifle bullet, higher than most missiles could reach, and for 24 years not a single one was ever shot down. But speed is not the interesting part. The interesting part is that the jet was actively trying to destroy itself the entire time it was flying, and the engineers had to let it. Nobody told the pilots that the aircraft they were about to fly was, in a meaningful engineering sense, broken on the ground. They found out during training, and the explanation they received was not reassuring. The SR-71 sat on the runway leaking fuel, not dripping, leaking visibly from seams along the fuselage and wing panels. Puddles formed beneath it. The ground crews treated this as normal because it was normal. It was, in fact, designed. And understanding why the most advanced aircraft ever built was intentionally designed to leak fuel on the ground is the first step toward understanding how it survived doing things that should have been physically impossible. The SR-71 was built to cruise at Mach 3.2, 3 times the speed of sound, approximately 2,200 miles per hour at altitude. At that speed, the air the aircraft is moving through cannot get out of the way fast enough. It compresses in front of every surface, and that compression generates heat. Not the modest warmth of a commercial aircraft at cruise, but temperatures that would melt conventional aluminum structures from the outside in. The leading edges of the SR-71's wings reached temperatures above 600 degrees Fahrenheit during sustained cruise. The cockpit windscreen reached over 600 degrees on its outer surface. See the aft fuselage, where the engine's exhaust and the aerodynamic heating combined reached temperatures approaching 1,000 degrees Fahrenheit. At those temperatures, the aircraft is not flying through air. It is flying through a thermal environment that treats the entire airframe as a heating element. Aluminum fails structurally well below those temperatures. The engineers at Lockheed's Skunk Works, the classified advanced development division that built the SR-71 under Kelly Johnson, knew this before they drew the first line. Their solution was titanium. The SR-71 is approximately 85% titanium by weight, a material that retains structural integrity at temperatures that would reduce aluminum to something with the consistency of warm toffee. Titanium was the right answer. It was also in the early 1960s and extraordinarily difficult to machine, weld, and work with at the precision required for an aircraft. The Skunk Works engineers spent years developing new tools, new techniques, and new processes just to fabricate the material that the design required. Early titanium parts failed during manufacturing at a rate that would be unacceptable by any normal production standard. The team refined the process until the failures became rare, then rarer, then essentially gone. The aircraft that resulted was built from a material that barely existed as a manufacturing proposition when the project started. Titanium solved the heat problem for the structure. It did not solve the heat problem for the dimensions of that structure. Metal expands when heated. A 107-foot aircraft made of titanium that heats from ambient ground temperature to sustained cruise temperature expands by roughly 11 inches in total length. Every panel, every seam, every joint in the aircraft has to accommodate that expansion without binding, cracking, or creating gaps that would compromise aerodynamics or structural integrity. The solution to this problem is the reason the aircraft leaked fuel on the ground. The fuel tank panels were manufactured with gaps between them, deliberate clearances sized to close up and seal correctly only when the airframe had expanded to its cruise temperature. On the ground, cold, those gaps were open. The fuel inside the tanks seeped through them freely. The aircraft was only properly sealed when it was flying at the speed that was trying to destroy it. Below that speed, it leaked. And the pilots took off knowing they had insufficient fuel for a long mission, climbed to altitude, accelerated to cruise speed, waited for the airframe to seal, and then refueled from a waiting tanker. Every SR-71 mission began with an airborne refueling. The aircraft could not take off with a full fuel load because a full fuel load on the ground would have created a lake of jet fuel beneath it. The fuel itself was not conventional jet fuel. JP-7 was developed specifically for the SR-71 because standard jet fuel would have auto-ignited, caught fire spontaneously in the heat environment of the aircraft's fuel tanks at cruise. JP-7 has an extremely high flash point and low vapor pressure, making it stable at temperatures that would cause conventional fuel to ignite without a spark. why it is so stable that the SR-71's engines could not ignite it with a conventional ignition system. The aircraft used a chemical ignition additive, triethylborane, a compound that ignites spontaneously on contact with air to start the engines. Ground crews injected a small quantity of triethylborane into the engine during startup. It contacted the air in the combustion chamber and ignited. The JP-7 followed. The entire startup sequence was, at its core, a controlled chemical reaction that would have been alarming to watch without knowing what was happening. With the knowledge, it was merely alarming. Here is the question that should have occurred to you by now, and if it hasn't, it means the full strangeness of this aircraft hasn't landed yet. The SR-71 was flying at Mach 3.2. The air in front of it was compressing and heating to temperatures that threatened the structure. The engines were ingesting that same superheated, compressed air and trying to burn fuel in it. A jet engine at Mach 3.2 is not operating in anything like the conditions it was designed for at subsonic speeds. The air arriving at the engine intake is moving so fast that if it entered the engine directly, it would extinguish the combustion entirely. You cannot burn fuel in an airstream moving at 3 times the speed of sound. The entire thrust equation breaks down. So how did the SR-71's engines produce any thrust at all? The answer is the inlet. And the inlet is, by any measure, the most sophisticated piece of engineering on an aircraft full of sophisticated engineering. The SR-71 used a mixed compression inlet system built around a moving spike, a sharp conical spike mounted at the center of each engine's circular intake opening. At subsonic and low supersonic speeds, the spike sat in a forward position and air flowed around it into the engine relatively normally. As the aircraft accelerated past Mach 1.6, the spike began moving rearward, controlled by the aircraft's inlet control system. As the spike moved, it created a series of oblique shockwaves, controlled compressions of the incoming air that slowed it progressively and raised its pressure and temperature in a managed sequence. By the time the air reached the engine face after passing through this shock system, it had been slowed from Mach 3.2 down to subsonic speeds, around Mach 0.4, and its pressure had increased dramatically. The engine was receiving air it could actually use. The inlet was doing more of the thermodynamic work of the propulsion system than the engine itself. At cruise speed, roughly 54% of the SR-71's total thrust came not from the engine's turbine and combustion, but from the ram compression and the flow management of the inlet system. The inlet control system that managed the spike position had to respond to changes in airspeed, altitude, and angle of attack continuously, moving the spike in fractions of an inch to maintain the shock system in exactly the right position. If the shock position moved out of tolerance, if the system failed to maintain the normal shock precisely at the inlet throat, the result was an unstart. An unstart occurred when the supersonic flow broke through the shock system and the inlet lost its ability to process the incoming air. The engine on that side effectively stopped producing thrust in a fraction of a second. At Mach 3.2, losing thrust on one side of a twin-engine aircraft produced a yawing moment, violent enough to slam the pilot's helmet against the canopy hard enough to cause injury. Early SR-71 pilots experienced unstarts regularly before the inlet control system was refined, and the experience was described consistently as being hit in the head with a bat while sitting in an aircraft that was suddenly trying to rotate sideways at 2,200 miles per hour. And the system could also cascade, one unstart disturbing the airflow enough to trigger an unstart on the other engine, leaving the aircraft momentarily on no thrust at all at an altitude and speed, where a recovery was possible but not guaranteed. The Pratt & Whitney J58 engines that powered the SR-71 were unlike any other jet engine in service. They were designed to transition between two fundamentally different operating modes as the aircraft accelerated. At lower speeds, they operated as conventional turbojets, with all the airflow passing through the compressor, combustion chamber, and turbine. At high speeds, 6 bypass tubes per engine opened and routed a significant portion of the intake air directly from the inlet to the afterburner section, bypassing the turbine entirely. This effectively turned the engine into a partial ramjet, using ram compression from the inlet rather than mechanical compression from the turbine to prepare the air for combustion. The J-58 was not a turbojet that happened to go fast. It was a hybrid propulsion system that changed its fundamental operating mode in flight, and doing so smoothly enough that the pilots felt a change in engine character rather than a disruption required engineering that had never been attempted before. The pilots who flew the SR-71 were not selected for their willingness to accept risk. They were selected for their ability to manage a workload that had no equivalent in any other aircraft in the inventory. The SR-71 had two crew positions, pilot and reconnaissance systems officer, called the RSO, seated in tandem in separate cockpits. Both wearing full pressure suits because the aircraft flew high enough that a sudden pressure loss at altitude would be fatal in seconds without them. The suits were the same type worn by NASA astronauts of the same era for the same reason. Above a certain altitude, the atmosphere provides insufficient pressure to sustain human physiology regardless of oxygen concentration. At the SR-71's cruise altitude of 85,000 feet, the atmospheric pressure is roughly 1% of sea level pressure. Without a pressure suit, the blood begins to boil. The cockpit the pilot occupied was small and dense with instrumentation. The SR-71 predated glass cockpit displays. Everything was analog gauges and mechanical indicators. The pilot monitored engine parameters, inlet spike positions, fuel quantity across multiple tanks that had to be balanced to maintain the aircraft's center of gravity within narrow limits, navigation systems, and the aircraft's position relative to programmed waypoints, all simultaneously. The RSO managed the reconnaissance sensors, cameras, radar systems, and signals intelligence equipment, and handled navigation backup and communications. The workload during the cruise phase of a mission was described by experienced crews as high but manageable. The workload during the acceleration phase, the refueling, and any unplanned system event was described as the kind of focused intensity that leaves no capacity for anything not immediately relevant to keeping the aircraft flying. The pressure suit created its own management burden. The suit was pressurized independently of the cockpit, and the pressurization altered the pilot's physical relationship with the controls. Gloves designed to maintain dexterity under pressurization still reduce the fine motor feedback that unpressurized hands provide. Reaching a control that was simple in ground testing required deliberate, practiced movement in the suit. Pilots trained extensively in suits before flying, and the training was designed specifically to make suit operations automatic, to move the cognitive load of working in a suit into muscle memory so that conscious attention could be directed at the aircraft. A pilot who had to think about how to reach a switch while also managing an unstart had already lost the margin that separated a recovered emergency from an unrecovered one. The SR-71 could not be caught. This was not an aspiration. It was a documented operational reality. Every missile engagement attempted against the SR-71 during its operational career failed. The aircraft's combination of speed and altitude put it outside the effective engagement envelope of every surface-to-air missile system it encountered. A missile launched at the SR-71 from directly ahead faced an approach geometry where the closure rate was so high that the missile's guidance system could not track and lead the target accurately. A missile launched from behind faced the opposite problem. The SR-71 was pulling away faster than most missiles could accelerate. The typical response when radar warning systems indicated a missile launch was recorded by pilots as "note the launch, note the bearing, maintain cruise speed and altitude." The missiles did not arrive. This happened more than once. The exact number of missile launches against SR-71s remains classified, but former crew members have confirmed the number is not small, and the result was always the same. The reconnaissance data the SR-71 collected per flight was extraordinary by the standards of any era. The aircraft could photograph 100,000 square miles of territory in a single hour of flight, an area roughly the size of the United Kingdom. The cameras operated through the aerodynamic heating environment of cruise by using quartz windows with specific optical properties that maintain transparency at high temperatures, and by housing the film in thermally isolated bays that kept it below the temperatures at which the emulsion would be damaged. The data the film recorded was processed after landing. But later variants carried systems that could transmit imagery during flight. A nation could begin a crisis, and SR-71 imagery of that nation's military dispositions could be in analysts' hands within hours of the decision to fly. The SR-71 was retired twice. The first retirement came in 1990, driven by budget pressure and the argument that satellites and other reconnaissance platforms had made the aircraft redundant. The operational crews who flew it disagreed with that argument, and events after the retirement produced some evidence that they were right. The aircraft was reactivated in 1995 when operational demands arose that other platforms could not meet. It was retired again in 1998, this time permanently, or as permanently as anything in the defense world ever is. The argument for retirement rested on cost. Operating the SR-71 was extraordinarily expensive, not primarily because of fuel or crew costs, but because of the maintenance burden imposed by the aircraft's extreme operating environment. Every flight subjected the airframe to thermal cycles that few materials were designed to handle repeatedly. The titanium structure expanded and contracted through a range of over 10 inches every single flight. The sealants used to make the fuel system functional at cruise temperature degraded with each cycle and had to be replaced. The inlet systems required inspection and calibration after every flight. The J-58 engines, designed to operate in a thermal and pressure environment that no other engine experienced, had service lives and inspection intervals that were far shorter than conventional power plants. The aircraft that could photograph 100,000 square miles per hour required hundreds of maintenance hours on the ground for each hour it spent in the air. The skunk works culture that built the SR-71 produced an aircraft that represented the absolute edge of what the physics and materials of its era allowed. Kelly Johnson's engineering philosophy, small teams, fast decisions, direct accountability, no bureaucratic buffer between a problem and the person who could solve it, enabled a development program that would have taken decades under conventional acquisition processes to complete in a handful of years. The first SR-71 flew in 1964. The aircraft it replaced, the U-2, had already been embarrassingly shot down over the Soviet Union. The need for an aircraft that could not be shot down was not theoretical. It was urgent. The skunk works delivered it. What the SR-71 required its pilots to accept was a set of risks that had no precedent in operational aviation. The aircraft was not dangerous in the way that early jet aircraft were dangerous, through mechanical unreliability or poor handling at normal speeds. It was dangerous in the way that exploring a genuinely new physical regime is always dangerous. The consequences of departing from the narrow operating band where everything worked were severe and in some cases not survivable. 12 SR-71s were lost during the program's operational life, not to enemy action, but to accidents, system failures, and the inherent risks of operating a machine at conditions where the margin between controlled flight and uncontrolled flight was narrow, and the altitude left little room for recovery. The crews who flew it did not describe the experience in terms of danger. They described it in terms of a particular kind of clarity, the focused, present tense attention that comes from operating a system that demands everything and returns something no other experience provides. At 85,000 feet and Mach 3.2, the curvature of the Earth is visible. The sky above is dark blue approaching black. The aircraft is moving fast enough that a city passes beneath in under a minute. The pressure suit is pressing against every part of the body. The engines are burning fuel at a rate measured in pounds per second rather than gallons per hour. The inlets are managing shockwaves with mechanical precision measured in fractions of an inch. The airframe is 900 degrees on its hottest surfaces and expanding continuously. And the aircraft is doing exactly what it was designed to do, existing briefly in a physical regime that nothing else could reach, and returning information that nothing else could collect. The SR-71 was retired because it was too expensive to operate. It was never retired because anything replaced what it could do. The satellites that were offered as its replacement orbit on fixed schedules that adversaries can predict and prepare for. The SR-71 arrived when it was sent, flew where it was directed, and could not be stopped. No aircraft currently in service can make all three of those statements simultaneously. The engineers who built it understood that what they were building would not be improved upon quickly. They were correct. 60 years after the first flight, but the performance numbers of the SR-71 remain beyond the reach of any operational aircraft in the world. The record it set for air-breathing aircraft speed, 2,193 miles per hour, was set in 1976 and has not been broken. It will not be broken soon. The physics that made the SR-71 possible also define exactly how hard it is to go faster, and every engineer who has looked seriously at the problem has arrived at the same conclusion the Skunk Works reached in 1964. You can do it, but the aircraft will spend the entire flight trying to destroy itself. The only question is whether you can build something strong enough, clever enough, and strange enough to survive that long, to survive that long, to survive that long.